Welcome to our exploration of tidal forces and their profound effects on celestial bodies. Tidal forces are a fascinating aspect of gravity, influencing not just our oceans but the very structure of planets, moons, and even stars. In this video, we'll unravel how these invisible forces shape the universe, from the gentle rise and fall of Earth's tides to the dramatic stretching of distant worlds. Let's begin by understanding what tidal forces are and why they matter in the grand cosmic dance. Tidal forces arise due to the difference in gravitational pull exerted by one celestial body on different parts of another. Imagine the moon's gravity tugging on Earth. The side closest to the moon feels a stronger pull than the far side, creating a stretching effect. This difference in force is what we call the tidal force. It's a subtle but powerful phenomenon, responsible for many dynamic processes in the cosmos. Understanding this concept is key to grasping the rest of our journey. Gravity is the fundamental force behind tidal effects. Every object with mass exerts a gravitational pull, but when two bodies are close, the difference in gravity across their diameters becomes significant. This is especially true for large bodies like planets and moons. The interplay of these gravitational forces leads to the stretching and squeezing we observe as tides. Without gravity, tidal forces simply wouldn't exist, making it the cornerstone of our discussion. One of the most familiar effects of tidal forces is the rise and fall of Earth's oceans. The moon's gravity pulls on Earth's water, causing it to bulge out on the side facing the moon and the opposite side as well. This results in two high tides and two low tides each day. The sun also plays a role, enhancing or diminishing the tides depending on its alignment with the moon. These daily rhythms are a direct result of tidal forces at work. Tidal forces create variations in the height of tides known as spring and neap tides. When the sun, moon, and Earth align, their combined gravitational pull causes especially high and low tides called spring tides. When the sun and moon are at right angles, their effects partially cancel out, leading to neap tides with less extreme differences. These cycles are predictable and have been observed for centuries, shaping coastal environments and human activity. Tidal forces don't just affect oceans, they can also influence the rotation of celestial bodies. Over time, tidal interactions can slow a moon's rotation until it matches its orbital period, a phenomenon called tidal locking. This is why we always see the same face of the moon from Earth. Tidal locking is common throughout the solar system and plays a crucial role in the evolution of planetary systems. Our moon is a classic example of tidal locking. Billions of years ago, the moon rotated much faster, but Earth's gravity gradually slowed its spin. Now, the moon's rotation period matches its orbit around Earth, so one side always faces us. This synchronous rotation is a direct result of tidal forces, and it's a phenomenon observed with many moons throughout the solar system. Tidal forces can also generate heat within celestial bodies. When a moon orbits a planet in an elongated path, the varying gravitational pull stretches and squeezes the moon, creating friction and heat. This process, called tidal heating, can melt ice and even drive volcanic activity. Jupiter's moon Io is the most volcanically active body in the solar system, thanks to intense tidal heating from Jupiter's gravity. Jupiter's moon Europa is another fascinating case. Tidal forces flex Europa's icy shell, generating enough heat to keep a vast ocean liquid beneath the surface. Scientists believe this subsurface ocean could harbor life, protected from the harsh environment of space. Tidal heating is the key to maintaining this hidden sea, making Europa one of the most intriguing worlds in our solar system. Saturn's moon Enceladus also experiences tidal heating. The gravitational tug from Saturn causes Enceladus to flex, producing enough heat to power geysers that shoot water vapor and ice into space. These plumes have been observed by spacecraft, providing clues about the moon's internal ocean and its potential habitability. Tidal forces are the driving engine behind this spectacular phenomenon. Tidal forces can sometimes be destructive. When a star ventures too close to a massive black hole, the difference in gravitational pull across the star can tear it apart in a dramatic event known as a tidal disruption event. The star's material is stretched and pulled into the black hole, releasing enormous amounts of energy. These rare but powerful events offer a glimpse into the extreme power of tidal forces. Roche Limit is the minimum distance at which a celestial body, held together only by its own gravity, can orbit another body without being torn apart by tidal forces. If a moon or comet crosses this boundary, it can be shredded into pieces, forming rings or debris. This concept helps explain the formation of planetary rings and the fate of objects that stray too close to massive planets. Saturn's stunning rings are a direct result of tidal forces. Many scientists believe that moons or comets that ventured too close to Saturn were torn apart by tidal stresses within the Roche Limit. The resulting debris spread out to form the planet's iconic rings. This process is a beautiful example of how tidal forces can both destroy and create new structures in the cosmos. Tidal forces play a crucial role in shaping the environments of exoplanets, planets orbiting other stars. In many cases, close-in exoplanets are tidally locked to their stars, with one side in perpetual daylight and the other in darkness. This has profound effects on their climates and potential habitability, making tidal forces a key factor in the search for life beyond our solar system. In binary star systems, tidal forces can transfer angular momentum between stars, affecting their orbits and rotation rates. Over time, this can lead to synchronized rotations or even the merging of stars. These interactions are complex but essential for understanding the evolution of star systems and the diversity of objects we observe in the universe. Tidal forces aren't limited to planets and moons, they also shape galaxies. When galaxies pass close to each other, tidal forces can strip away stars and gas, creating long streams and tails. This process, known as tidal stripping, plays a major role in galaxy evolution and the formation of new structures in the cosmos. When two galaxies collide, tidal forces can pull out long streams of stars and gas known as tidal tails. These spectacular features are visible in many interacting galaxies and provide evidence of the powerful gravitational interactions at play. Tidal tails can stretch for thousands of light-years, reshaping galaxies over cosmic time. Star clusters orbiting within galaxies are also subject to tidal forces. As they move through the galaxy, tidal interactions can strip away stars from the cluster, gradually dispersing them into the galactic field. This process helps explain why some clusters appear elongated or have lost many of their original stars. Black holes exert some of the strongest tidal forces in the universe. As objects approach a black hole, the difference in gravity across their length becomes extreme, leading to a process called spaghettification. This dramatic stretching can tear apart stars, planets, or even unlucky spacecraft that venture too close. Spaghettification is the ultimate consequence of tidal forces near a black hole. As an object falls toward the event horizon, the gravity at its leading edge is much stronger than at its trailing edge, stretching it into a long, thin shape. This process is fatal for anything caught in it, demonstrating the incredible power of tidal forces in extreme environments. Tidal forces are responsible for the formation and maintenance of planetary rings. When moons or comets come too close to a planet, tidal stresses can break them apart and the debris forms rings. These rings are constantly shaped and confined by the planet's gravity and the gravitational influence of nearby moons, creating the stunning structures we see around Saturn, Jupiter, Uranus, and Neptune. Comets that pass close to massive planets can experience intense tidal forces. These forces can break the comet apart, creating spectacular displays of debris and sometimes forming temporary rings. The breakup of comet Shoemaker Levy 9 by Jupiter's gravity is a famous example, illustrating the destructive potential of tidal forces. Asteroids can also be affected by tidal forces, especially during close encounters with planets. These interactions can alter the asteroid's shape, spin, or even break it apart. Studying these effects helps scientists understand the history of our solar system and the risks posed by near-Earth objects. Tidal forces can influence the atmospheres of planets and moons. For example, tidal heating can drive volcanic activity, which releases gases and shapes the atmosphere. On some exoplanets, tidal locking creates extreme temperature differences between the day and night sides, affecting atmospheric circulation and weather patterns. Tidal forces can make or break the habitability of a world. On one hand, tidal heating can provide energy for subsurface oceans, as seen on Europa and Enceladus. On the other, extreme tidal locking or tidal disruption can create harsh conditions. Understanding these effects is crucial in the search for life beyond Earth. Tidal interactions can cause planets and moons to migrate over time. As energy is transferred between rotation and orbit, bodies can move closer together or farther apart. This process has shaped the architecture of our solar system and continues to influence planetary systems across the galaxy. Tidal forces can lock moons and planets into orbital resonances where their orbits are synchronized in simple ratios. This can enhance tidal heating and lead to complex gravitational interactions. The Galilean moons of Jupiter are a classic example, with their orbits locked in a 1-2-4 resonance that drives intense tidal effects. Tidal forces are gradually slowing Earth's rotation. As the moon's gravity pulls on Earth's oceans, it creates friction that transfers energy from Earth's spin to the moon's orbit. This causes our days to lengthen over millions of years and pushes the moon slowly farther away. It's a subtle but measurable effect of tidal interactions. The moon is moving away from Earth at a rate of about 3.8 centimeters per year, thanks to tidal forces. This process, known as lunar recession, is a direct result of the energy exchange between Earth's rotation and the moon's orbit. Over billions of years, this will continue to alter the dynamics of our planet-moon system. Tidal forces can even influence geological activity on Earth. The gravitational pull of the moon and sun slightly deforms Earth's crust, and in some cases this can trigger earthquakes or volcanic eruptions. While the effect is small compared to tectonic forces, it's a reminder of the interconnectedness of celestial mechanics and planetary processes. On some moons and planets, tidal forces are the main driver of volcanic activity. The constant flexing and heating caused by tidal interactions can melt rock and ice, fueling eruptions and shaping the landscape. Io's volcanoes and Enceladus geysers are prime examples of tidal volcanism in action. Tidal heating can influence the magnetic fields of planets and moons. By driving internal motion and convection, tidal forces help sustain magnetic fields, which protect atmospheres and surface life from harmful radiation. This connection is especially important for understanding the habitability of distant worlds. Some scientists believe that tidal forces played a role in the origin of life on Earth. The regular rise and fall of tides created unique environments along coastlines, concentrating organic molecules and providing energy for chemical reactions. Tidal pools may have been the cradle for the first living organisms. Tidal forces have influenced the evolution of life on Earth. The changing tides shaped coastal habitats, driving the adaptation of plants and animals to both land and water environments. Many species have evolved to take advantage of tidal cycles, demonstrating the far-reaching impact of celestial mechanics on biology. Humans have long harnessed tidal forces for practical purposes. Tidal mills, tidal energy, and navigation all rely on the predictable movement of tides. Understanding tidal forces has been crucial for coastal communities, shipping, and the development of renewable energy sources. Tidal forces can influence climate by affecting ocean currents and mixing. The movement of tides helps distribute heat and nutrients throughout the oceans, impacting weather patterns and marine ecosystems. This subtle but important effect highlights the interconnectedness of celestial and terrestrial processes. For centuries, sailors have relied on their understanding of tides for safe navigation. Tidal charts and predictions are essential for entering and leaving harbors, avoiding hazards, and planning voyages. The regularity of tidal cycles, governed by celestial mechanics, has made them a reliable tool for human exploration. Tidal energy is a promising source of renewable power. By harnessing the movement of tides, engineers can generate electricity with minimal environmental impact. Tidal power plants are already in operation in several countries, demonstrating the practical benefits of understanding and utilizing tidal forces. Space missions must account for tidal forces when planning trajectories and landings. The gravitational influence of planets and moons can alter spacecraft orbits, requiring precise calculations. Understanding tidal effects is essential for the success of missions to the Moon, Mars, and beyond. As we look to explore the solar system and beyond, tidal forces will remain a key consideration. From landing on icy moons to searching for life in subsurface oceans, understanding tidal effects will help guide our discoveries and shape the future of space exploration. Tidal forces have inspired countless stories in science fiction. From planets with extreme tides to worlds torn apart by black holes, writers and filmmakers use tidal effects to create dramatic and imaginative settings. These stories reflect our fascination with the power of gravity and the mysteries of the universe. Artists have long been inspired by the rhythms of tides and the cosmic forces behind them. Paintings, sculptures, and music capture the ebb and flow of water, the pull of the moon, and the grandeur of celestial mechanics. Tidal forces connect science and art, reminding us of the beauty and wonder of the universe. Throughout history, cultures have woven the tides into their myths and legends. The moon's influence on the seas has inspired stories of gods, monsters, and magical events. These tales reflect humanity's deep connection to the rhythms of nature and our curiosity about the forces that shape our world. As our understanding of tidal forces grows, so does our ability to harness their power and mitigate their risks. From protecting coastal cities to exploring distant worlds, tidal forces will continue to shape our future. By studying these cosmic interactions, we gain insight into the workings of the universe and our place within it. Tidal forces are a testament to the subtle yet profound influence of gravity across the cosmos. From shaping planets and moons to inspiring art and mythology, their effects are everywhere. As we continue to explore and learn, tidal forces remind us of the interconnectedness of all things in the universe. Thank you for joining this journey through the wonders of tidal forces and their effects on celestial bodies.